the problem we will solve now is this. It's again, let's give it a name. Again, mass or block on a moving wedge, but with momentum and energy considerations. Okay. So the problem is this. We have this wedge. No friction, mu equals 0 everywhere. And this falls down, slides down, and sometime later, this was its original position. It has come down to here, and this vertical distance is h. Horizontally, it moved to the right by L. Theta. So when it has come down on the wedge by a distance h in the vertical direction, what is the speed of the wedge? Okay. So this problem can be stated simply as a momentum and energy problem. Let's look at this system. Isolate our system, and let's look at the external forces on it. And as you see, there are no horizontal forces. Although they interact, these two interact, there is no external agent that pushes and pulls our system in the horizontal direction. Therefore, the delta P total is 0 because there is no external force. Therefore, the initial, let me call it x. Okay. So initially it was 0. Finally, we have m going here with u, the wedge, and m going to the right with vx. This is the speed of m in the horizontal direction with respect to ground. So obviously, mu is equal to m vx. Okay, that's the momentum conservation. And how about the energy conservation? Now, what sort of energies do we have? First, we have let's write here. Let's make a table. This is the kinetic energy of mass m, small mass block. There is no friction, therefore the energy in the mechanical motion is conserved. So let's write what sort of energies we have. And before writing the energies, let's notice for whom are we writing these energies? We are writing the energies for an observer on the ground. So here's our observer on the ground. Okay. So there is the kinetic energy of the block, small block, and the gravitational potential energy of the block. And since this wedge is not going up and down, it can only have kinetic energy. So the kinetic energy of the wedge, Km. So initial energy is, well, this is the gravitational potential energy, mgh. And both of them are at rest, 0, 0. And E final, since we took this as the reference point of the gravitational potential energy, it is 0. This has 1/2 mv square. This is velocity with respect to ground, everything with respect to a ground observer. And this has 1/2 mu square. And since there is no friction, therefore, initial energy is equal to the final energy, or mgh is equal to 1/2 mv square plus 1/2 mu square. Now, V and U are related in this way. If I write this thing as V prime, the velocity of the block with respect to wedge, so that it makes an angle theta. So this is the velocity of the wedge with respect to ground. So mass m with respect to wedge. This is wedge with respect to ground. And this is mass m with respect to ground. Okay? So this is V. We see that as far as magnitudes go, V prime cosine theta minus U is Vx. And V prime sine theta is Vy. So let us write, for example, and also from here and here, for example, mu is equal to m Vx. So we insert this, V prime cosine theta minus U. Therefore, V prime is equal to m plus m U divided by m cosine theta. Now, let's write this one, because finally we want to find U. So let me write 1/2 mv square. V square is equal to for Vx, I insert this, V prime cosine theta minus U square plus 1/2 m V prime sine theta square equals the square of this plus the square of this term will give me 1/2 m V prime square. Then I have 1/2 2m V prime cosine theta times U plus 1/2 m U square. And m V prime cosine theta is m plus mu. So that this is equal to 1/2 m V prime square minus 1/2 U square 2m plus m. This is a minus sign, this is a plus sign, so this comes with a minus sign. So it is 1/2 m V prime square minus 1/2 U square Okay, I will erase what I don't need. I used these things before, so I'm erasing this. Let me write this again. 1/2 m V square is equal to 1/2 m V prime square minus 1/2 m plus 2m U square. So the energy was this thing plus 1/2 mu square, and let me add 1/2 mu square. So this is the initial energy, which is mgh equals, if I add 1/2, so here I have minus 2m, I am adding m, one of them cancels, so 1/2 mv prime square minus m plus m 1/2 u square. I have to keep it, and now I will insert for v prime this thing. Equals 1/2 m the square of that, m plus m square u square over m square cosine square theta minus 1/2 m plus m u square. Now I can erase this part. So mgh equals, I have 1/2, I have m plus m common factors, u square m plus m minus m cosine square theta divided by m cosine square theta. This is m 1 minus cosine square theta, which is sine square theta. So u square is 2 m square gh cosine square theta divided by m plus m times m plus m sine square theta, and u is just the square root of that. So square root of that, u equals square root of u square. This is 1/2. So we are finished. This is the, so if this block drops in the vertical direction by a distance h, by sliding over the thing, as it slides down, it's of course applying a force on the wedge, and the wedge is moving to the left, in fact accelerating, and at the end of a drop by distance h or height by h, the velocity picked up by the wedge is this. Let's check our answer. First, is it giving us the dimension of a velocity? So dimension u equals, this is m squared divided by m squared. I'm writing just the dimension, so masses cancel. G is L over T squared. H is L. Cosine without dimension, 1/2. So these things. So I have length over time. Okay, so dimension is velocity. Second, let's check, does it give us a expected limit? A limit that we know offhand. And it is when theta is like pi over 2, then here is your block. And of course, it will simply fall down and u should be 0. And indeed, if you put theta is equal to u is equal to 0, if theta is equal to pi over 2. Okay. So this was a straightforward problem that can be solved by the conservation of momentum and energy. But there's an interesting aspect to this problem, and I want to go over that very quickly. I will erase everything except these two relations. The question is this. What if we put the observer on the wedge? So if you put the observer on the wedge, how does the energy equation look like then? Okay. So for him, so what energies do we have? He has I will write K prime m, the kinetic energy of the mass m, and the potential energy gravitational of m. The wedge is not moving up and down, so no gravitational energy. Okay, and there is no kinetic energy of the big mass m because his observer is on the wedge. However, remember, because if you are on the wedge and the wedge is accelerating to the left with acceleration a, there is a force to the right by a. So if you go down, if the gravitational force is constant down with acceleration g, you associate with it in potential energy mgh. We have a constant acceleration to the right, so and it goes down by distance l. So let's say u prime m ghost or fictitious. On the wedge. So E prime initial, this is 0, this is mgh, this is mal. E prime f, this is 1/2 mv prime square, this is 0, and this is 0. And h and l, of course, are related. This angle is theta, so h over l is tangent theta, or l is h over tangent theta. Okay? So we will write mgh plus mal is equal to 1/2 mv prime square. And mgh is equal to 1/2 mv prime square minus mal. Now, if we compare this equation with that, we find that mal, which, by the way, is the work done by the fictitious force, that's equal to 1/2 m plus m from here, u square. Let us check that, I can erase the graphs now. Let us check that this agrees with our previous result. If you look at, for example, YouTube, mass on a moving wedge, where we solved the dynamic problem, namely we found the accelerations a, and a prime. There a is mg cosine theta sine theta divided by m plus m sine square theta. Let me just insert that. mal, so m times this a, mg cosine theta sine theta divided by m plus m sine square theta times L. L is h over sine theta over cosine theta, so cosine theta is here. That's equal to m sine theta is cancelled, So m squared g h cosine squared theta divided by m plus m sine squared theta. That's equal to 1/2 m plus m u squared. I don't need to do the algebra. If you multiply by 2, divide by m plus m, and take the square root, it's exactly this result. Okay? Finished. Thank you.